Let's read this question. It says g is continuous on this interval and g square is integrable on this interval from a to b, and we are given integration of g square from a to b is 0, and now we are asked to prove that g hash 0 for all x belonging to this interval. This is what we have to prove, and these three things are given to us. Okay, now we have understood the problem. Now let's understand the importance of each of these conditions. Okay, so let's read out first thing. It says g is continuous on this interval. Okay, so what is the importance of this first line? Okay, suppose I was not given this. I was only given this much problem. I was given g square is integrable and this condition, and I was asked to prove this. Well, then this would not have been a valid problem. You know why? Because suppose g is not continuous, then I can construct a function which satisfies this property, not identically equal to 0 in this interval, and it's not very hard to construct such a function. I'll give you one example. You can define gx to be equal to 0 for all x belonging to a to b except at points c and d, and at c you can give it any value, say 2, and at d you can also give it any value, say 5. So this function right here is not identically equal to 0, but integration of this g square from a to b will be 0. You know why? Because this would not make difference in integration. Integration at a particular point is 0. So I can write this as this: a to b g square is, say, a lies first, then c lies, then lies d, and then lies. So I can write this as integration from a to c g square plus d g square plus d to b g square, and this I know is 0. Function is 0 for all values between a and c except at c, and at one point integration value is not affected. We can skip the value of g at one particular point, which is c. So this is 0, this again is 0, and this too is 0. So this entire thing will be 0. So this function of mine satisfies this property, and g square is also integrable. So that what was the so this indicates the importance of this first condition. G has to be continuous. If g is not continuous, then from this information alone you cannot say g is identically equal to 0. Okay, now let's come to the second point, second condition: g square is integrable. What's the importance of this condition? Well, this condition is important for this equation to make sense. How can you integrate a function g square if you don't know it's integrable or not? It's a fair question. You may have encountered till now functions that are all integrable, but there exist functions which are not integrable, and I will give you an example of one such function. Okay, so I define my f as, it's a very famous function. Take 1 minus 1 for all x belongs to rational numbers and x belongs to irrational. This function is not, or what should I say, integrable. This function is not integrable. So, well, you may say its square is integrable. That is true, but suppose I define f square is this way. So now f square is not integrable. but f square cannot be minus 1, so you can take it to be, I don't know, say 2. F square is this is a perfectly valid function, and f square is not integrable. So there exist functions which are not integrable. Alright, so that's what was the importance of this second condition, that g square is integrable. This assures to us that square is not a function of this sort. I mean the functions which are not integrable, this is not integrable, but g square is given to be integrable, and that's why this equation makes sense. Alright, so you got the importance of first two conditions that are given to us, and the third one is just the information that is provided to us that the integration of g square is 0. In using this, we have to prove this. Also the first two conditions, as you saw their importance. Okay, so how do we do that? We do that in the following manner. Okay, solution. Now I know that g is continuous on a to b, which implies g square is also continuous on a to b. And we know that for a continuous function it's easy to construct an antiderivative. How? In this way. We define capital Gx to be a function which is in this way: a to x g square x dx, x belong to a to b. And we know from fundamental theorem of calculus that the derivative of gx is g square x. So since g square is continuous, we know how to construct an antiderivative of g square through fundamental theorem of calculus. We know this, it's easy, and we also know from fundamental theorem of calculus of such functions is this. Alright, we know this much now till now. Okay, and now we can see that capital G derivative is g square, which is greater than or equal to 0. From here it implies that g dash x is increasing, but it's increasing, but g of a, what can you say for what g of a could be? G of a is integration from a to a, which is 0, and g of b, as given in the problem, g of b is integration from a to b, g square dx, which is given to be 0. So that too is 0. Now can you say something from these three information? What can you say? We have a function from a to b which is increasing, but function at a is 0, and it's increasing, not strictly, but it means that it cannot go below 0. Either it has to go above 0 or it can remain at 0. So it's increasing. The moment it goes up, it cannot come down. Either it has to continue with the same value or it can afford to go up. But we know function at b is also 0. So now if it takes any positive value, then it cannot take again it cannot come back to the value 0. So it has to remain at 0 throughout this interval. So from these three information, I can say that this implies gx is 0 for all x belonging to this interval. And since gx is 0 for all x, its derivative also has to be 0 for all x belonging to a to b. I know what the derivative of g dash x is. I know it's g square x. So g square x is 0 for all x belonging to 0, and if g square x is 0, then gx also has to be 0. for all x belongs to 0. And this is how we prove this problem. For many of us, it might look trivial from this condition that it can directly follow this. But as you have seen the importance of continuity of G, without the continuity of G, this will not follow. And we have also seen the importance of this condition, because if G square is not integrable, this does not make sense. And how to rigorously show that from this it follows this. And this is what is tested in your ISI examination. Such problems you will see coming in the paper, and we'll bring more such conceptual videos. All right.